So John, he couldn't be here for this seminar, so thank you for coming. I guess that's the way it's starting usually. Suhasini, she's going to talk about Fourier-based statistics for irregular spatial data and application to testing for spatial stationarity, and inference of change points and other vaguely relevant stuff.
So thank you for being here. I sort of forced myself upon you guys, and they had to quickly look for a time, and this was the slot they found. Okay, so unfortunately I have no change points in this talk whatsoever. So this is why I'm vaguely related to all this, but I am looking at, the objective is looking for non-stationarity. So I guess this is where the vaguely related stuff is coming into play here. So to give you some background, basically, well, my motivation, which is the main objective of this actual talk, is about testing for spatial stationarity. But when I was working in this area over here, I saw that you could play around with a whole bunch of statistics. They're not necessarily new, but it brought out, in my opinion, quite nice results. So let me start with the motivation. I have two motivations. I start with the altruistic motivation first. So basically what we have is a spatial random field. Okay, so I'm drawing it so you have some idea of what all the parameters are involved. This is meant to be a square, by the way, though it looks like a rectangle. And basically, so the spatial random field is in a domain, and we'll call it minus lambda over 2, just for technical reasons, to lambda over 2. So the length of the domain is lambda, and the height of the domain is lambda. So this is a sort of a big cube in some sense. And what we do have are observations on this spatial random field, but they're irregularly sampled. And this is somehow important for what I'm about to do. Okay, so what we do is have spatial random field, and we have locations which are irregular on spatial random field, and on there we have our spatial observations, and that's what we observe. Okay, and we have n of those, so we have n observations on this field over here. And of course, the spatial covariance function, if we don't put any constraints and make any assumptions on such a stationarity on the covariance structure, is simply going to be a covariance of the two locations, say S1 and S2 over here. So I take the covariance, it's going to be a function of those 2 points over here. Of course, in most situations, this is just too much flexibility in the whole model. So one approach is to at least assume some sort of stationarity. Okay, so rather than the covariance function being a function of just this point and this point over here, we just take the distance. I mean, not the distance, the difference between the two. So S1 minus S2. Okay, so this is covariance stationarity. And so one reason we would do this is our ultimate aim would be to do something like spatial predictions, or do prediction at locations which are not there. And if we were going to do something like find the best linear predictor, we need the covariance structure of this spatial random field. Okay, so if we are assuming something like, so what sort of models would be fitted? And here I feel a bit like I'm joking. I'm trying to explain to you something I don't understand so much. But typically, what is fitted to these sort of to these type of data over here will be something like a Matern covariance. Okay, and so you see now that the covariance is basically the distance, the Euclidean distance between the 2 points. Okay, or you could even generalize this to what is known as the anisotropic Matern covariance, and now it's like a deformation of that distance in some sense. But regardless of, but both these examples here basically show you that the underlying this assumption is a stationarity. That basically means that the covariance between the 2 points is simply a function of the difference. Okay. Well, okay, so now you have to think, okay, well, what happens if this assumption is violated? What happens if our underlying field is actually not stationary? Then it would basically mean that our predictors are unreliable. So our question that we should be asking ourselves is, how do I go about checking this assumption? How do I, in some sense, test for spatial stationarity? And there have been some work in this area. One work has been done for spatial random fields not on irregular spacing like this, but on a grid, has been done by Fuentes. I cannot say her name properly, but Fuentes in 2006, and she defined a procedure that was based upon testing for stationarity on irregular grid. And her procedure was basically based upon getting your grid, trying to estimate the locally the covariance structure, and then making comparisons. Okay, and then Mikyung Jun and Marc Janton, who's in the audience, also propose a method for testing for spatial stationarity too, but theirs is now on a set which is also on a lattice, but on a more complex lattice, so basically it's on a sphere observed over time. I think their approach is also based upon making a comparison. I hope I'm right, yeah?
Yeah, but I mean, it's not necessarily on the lattice.
No, it's not. Oh, so the spatial domain is irregular spaced, yeah?
It can be.
Yeah.
But in some cases, you have replicates through time.
So you have more information. Yeah. Okay, sorry, I was wrong there. Okay, so I made a mistake in this point over here. So, okay, so what I want to do is look at an alternative approach. I'm not necessarily a better approach, but I want to look at an alternative approach for a regular space. And in order to do that, I look at so try to get my motivation from time series, which is my principal area of research. So this is my not altruistic reason for this research. When I started this, I thought it was, I have worked some time on testing for stationarity for spatial time series, for time series, and this is the sort of properties I was using there. And at the time, I thought I could immediately transfer these areas, these properties to the spatial domain. I was wrong. So, but I was hoping you could. And so let's just do a summary of how to test for stationarity within time series, just one or two slides on that. So one way of testing for stationarity is look at the sort of intrinsic property of stationarity, at least in the time series context. So in the time series context, what do you have? You have a series of observations observed over equally spaced time, okay? And if you take the DFT of it, okay, so discrete Fourier transform, okay, which is defined as this object over here, and you look at what's known as the Fourier, or fundamental frequencies, which is basically, for a time series, you essentially, you get the, you get 0 to 2 pi, and then you partition it up into a grid where each length is 1 over t. So these are the fundamental frequencies. So you're making one transformation from the time domain into the frequency domain. Then if a time series is second order stationary with some additional assumptions on the covariance structure, one can basically show that the correlation structure between the DFTs satisfies the following property, and this thing over here. You can see that the variance of this quantity over here is basically, if you don't know what this is a spectral density function, okay? And if the frequencies are different, so two different frequencies, you find that you get pretty much near correlation. So essentially, if your time series is relatively large, they're almost uncorrelated. Okay, and just in case you haven't, I'm sure pretty much everyone knows what this is, but this is a spectral density function, which is basically the Fourier transform of covariances. Okay, so basically, this is a sort of property that's somehow very much intrinsic to the principle of stationarity, and you can show that if the time series is actually non-stationary, that basically means the covariance structure changes over time, which means now if you take the covariance between two different time points, it doesn't depend upon the lag, it depends upon those two time points itself, then you do not have this, non-correlation structure anymore. And so basically what we did was we used this property over here to basically define a sort of portmanteau test for testing for correlation within the frequency domain, which basically meant that in the time domain, the time series are stationary. So this is work I worked on, and the question for me was, okay, so you get sort of nice results for time series. Can we get good results for spatial domain, but even harder? I mean, spatial domain, these things also hold if it's in a grid, but what I was looking for was what happens if you're not on a grid, but your data is irregularly sampled.
So your papers they are for the equispaced case, is that right?
But these two cases, time series,
Yes.
for equispaced, yeah.
It's already in that setting. And can you do, before going to spatial, can you do the time series?
For equally spaced?
Non-equally spaced?
Yes, you can if this approach, because this
Right.
yeah,
Yes.
yeah, you can.
But even, I mean, there's a step before going to the two-dimensional index.
Well, okay, so for me, when I started doing all this, I did it as a time series, but the only thing, it depends on your sampling scheme. Okay, and I have described to you the sampling scheme I'm using. If you use something like a Poisson sampling, I think it still works, but things get a little bit awkward. What I'm assuming is uniform sampling. But if I'm doing on the 1D case, it's uniform sampling on the 1D case I'm working on. So basically, so that's what I want to do. I want to see whether I can try to transfer these properties over, in particular, define a test for spatial stationarity based upon looking at correlations within the DFT. So basically, that's what I want to do. So, but the first thing is things need to be done is to first define the Fourier transform for a spatial random field. It's not exactly obvious, it's not in fact unique how this should be done. In the time series case, it's very clear, it's been done for the past 60, 70 years. In the spatial domain, it's not clear. So we'll use a specific definition of it, okay? And then you have to find out, okay, so once I've defined this Fourier transform, where do these so-called fundamental frequencies lie? So how do I get those frequencies out in which that in the spatially stationed setup, I get near uncorrelatedness. So that's what we'll do. And once we have this, we'll be able to define the test statistic. And then I'll take a small step back and look at sort of general framework of these statistics and give you a flavor of some of the sampling properties of this statistic, then come back again and use these sampling properties here to obtain the asymptotic sampling properties of this test statistic. And then finally, I'll also try to, and that's under null of stationarity, and then I look at what's happening with non-stationarity, so try to get a feeling of what things are working out in non-stationarity. And then very finally, unfortunately, this work is based upon sort of 2 little papers I've written, but I'm working on the simulations. I have no data or simulations right now. I'm just in the process of coding it, but I'll give you some problems with implementation that I've just uncovered. Okay, so that's good. Okay, so let's try to define. So our objective is our data, remember, is this thing over here. This is our data, this is what we have. So this is irregular space. And now what I want to do is now try and transfer the classical DFT to now to the irregular spatial domain. So from here, what I'll use is I'll basically, in my opinion, this DFT, which has been around, this Fourier transform, which has been around now for a couple of years, Matsuda and Yajima in a beautiful paper in JRSSB, and Lahiri in a later paper, they basically defined their Fourier transform as this thing over here. So essentially what they have is that it's like the Fourier transform of the observations, but you replace the time index by this location index times the frequency. It's very much analogous to the DFT in the classical case. The normalization is not so clear. So basically, they look at the space of the random field. They have the root 2, which is analogous to the thing and divide by sample space. This sort of becomes clear when you start playing with the calculations, why this normalization exists. Okay, but in my opinion, the precursor to this was actually a paper by Masery in IEEE, where basically he defines also a sort of a Fourier transform in the time series domain, but on the continuous time where you only have Poisson sampling, and he used something similar, but without that sampleization. Okay, so this is our Fourier transform, and so what we want to do is try to find out the point in which you get the near uncorrelatedness. Okay, so in order to make everything simple, and this is basically how I do my calculations, I did it all on the case of the time series. So basically d is equal to 1, and then you can relatively straightforward generalize that idea. Okay, so in the one-dimensional setup, this is what the whole thing looks like. Okay, so same thing as here, but we're in the 1D setup. So now our spatial domain are basically irregular observations here. Okay, so that's kind of what I want to do now. And so now what we want to do is try to find the analogous version of 2 pi k over t, but now for the spatial domain. All right? And so basically, it's relatively straightforward to show this, and I'll just briefly explain to you where everything comes from. I'm not going to give you a big calculation, don't worry. But this whole thing come up. Oh my goodness gracious, what's happened?
No, you need not to put it up because it's
working anymore.
Okay, that's fine. Then I'll cut it down and it'll start working again. It's 0, 1, I assume.
Let's hope so.
So, okay, so just quickly to show you, because I mean, in some sense it gives you an idea what's happening. I'll be very fast. I know that you don't want to hear the article, but suppose you were to work out the covariance between two locations, okay? Basically, and this is where all the scaling factor comes out, which is why I explain it to you now. This is basically 1 over n squared, and then this is the expectation of this dft, which is 1 to n, and then it's zsj1, zsj2, e to the I sj1, omega 1 minus I sj2, omega 2. Okay, so quickly to explain to you why we have the n squared over here. Basically, you can see, so long as j1 is not equal to j2, we have identically distributed random variables. Okay, so we can just reduce this whole, when the case that j is equal to j1, that's a little bit awkward, but we don't worry about it. So, but now this basically becomes 1 over, this becomes lambda, expectation of z s1. This is probably very trivial for all of you. E to the I s1 omega 1 minus I s2 omega 2. Okay, so you have this thing over here. And now I'm going to start making an assumption here. I'm going to make the assumption, okay, I have to explain this already, that the way the sampling is working is going to be uniform on the spatial random field. Okay, so S1, S2, S3, S4, so forth, is a uniformly distributed in this random field. Okay, you can quibble on this point, but this is the assumption I'm going to be working. I will tell you later problems that would arise without non-uniformity and how you can overcome it. But for now,
Can I ask, Matsuda and Yailima, did they use such a uniform distribution?
no, they use general.
I see.
Yeah, they use general situation. And I'll explain to you what happens in that case over there. There's certain things that happen, but the property I'm about to give you, you can probably imagine no longer holds. Okay. So, and so now if you work this whole thing out, this whole thing basically becomes a double integral, because this is uniform, remember, S2 minus lambda over t lambda over t, and then this is cs1 minus s2 e to the I s1 omega 1 minus omega 2 e to the I s2 omega 1. I probably messed up big time. Omega 2 ds1 ds2. Okay, so this is just rearrangement of the indices, and the thing that happens essentially is that now you start to make a change of variable. You say, okay, let s1 minus s2 equals some u. Okay, change of variable, very nice. And then you can start pulling things out. So what happens is that, let me pull things out a little bit. This whole quantity then becomes equal to e to the I s1 omega 1 minus omega 2 here. And then this thing over here is u. And then this thing over here, oh dear me, this goes away.
There is an eraser, I think.
Oh yes, that's true. You can see my students really hurt when I teach. Okay, so this thing over here becomes cu e to the I u omega, I think it's just to see. So this is u omega 1. Okay, 1 second. E to the I u omega 1. And this is du. Okay, so this thing over here, so, and this is ds1. Okay, so, okay, now, and it's a bit of a mess, and I apologize about that, plus some error of 1 over lambda. Okay. So what basically happens is this is really a Fourier transform of the covariance. So this thing over here is approximately equal, by definition, to the spectral density, for example. That's Fourier transform of the covariance. Now, what we have is the most interesting part, and this is basically the Fourier transform of the indicator function. Okay? Now, you know that if you take the Fourier transform of the indicator function, if omega 1 minus omega 2, so if you let omega 1 minus omega 2, this thing over here becomes 2 pi r over lambda, then we have basically the frequency in which this Fourier transform is equal to 0. So essentially, it's very, very obvious, and you're looking like it's completely clear, and I really hope that this thing comes on now, and it doesn't, of course. Oh, yes, beautiful. Okay, hello. Okay. Hello. Maybe I have to wake my computer up. Oh, yeah, now I have to wake the computer up. Okay, come through. There we are. So basically what you have is that this whole thing over here is, you get this very basic calculation over there. So essentially, so long as you basically have, you choose your so in this case over here, it says if the distance between the two frequencies is basically a multiple of 2 pi over lambda, and lambda being now the spatial domain, then you have near uncorrelatedness, okay? Which is very obvious. So now what it says, okay, rather than use, now what we want to do is we define now our fundamental frequencies to be 2 pi k over lambda. So no longer time, it's lambda, and now k is equal, well now it's not clear, but k plus 1 to whatever. And that is our fundamental frequencies. And then we have this uncorrelatedness property of the DFT. So it's kind of interesting because now in the Fourier spatial domain, we have this sort of irregular sampling. But now what we do is we have sort of analogous version in the Fourier domain where we sort of gridified our data. We put it onto a grid, okay? And essentially on the grid we get, okay, we don't get complete uncorrelatedness, but we get near uncorrelated. So we've gone from irregular space in the free spatial domain to a grid on the frequency domain, but the distance between the grid is 1 over lambda. Okay, so this is kind of what we have now, okay? All right, so that's basically what we see. And if you look in terms now, this is I did for the 1D case. If you look now in the general case, you have basically the following result. So now we're in sort of a D-dimensional setup. The same idea, you do a gridding on that, but the Fourier transform between 2 points on the grid is basically, if the variance of this is basically the Fourier transform, the spectral density, okay, I mean the Fourier transform of the covariance. And if you have two frequencies which are far different points on the grid, then it's going to be 1 over d minus b. And to explain to you what I mean by that, it says it's looking for, so basically, if you treat this as k1, k2, and this is k1 plus r1, k2 plus r2, that distance there is, the 2 points are completely different, so the level of uncorrelated is 1 over lambda squared, whereas if you looked between here and here, because one coordinate is the same but the other one is different, it's going to be 1 over lambda. So that's what happens in the higher dimensions. Okay, so then the question is, okay, what happens now if we're in the non-stationary setup? Do we get a different result? And then that we want to sort of exploit that if we do. And so in order to do that, what we'll do is we'll sort of try to sort of define the Fourier transform in the non-stationary setup. So in the non-stationary setup, okay, you have two locations. You look at the covariance between two locations. And for simplicity, again, I do this in the 1D setup just because it's notationally much easier to write down. And in this situation over here, you look at the covariance between two situations. So it's C S1, S2, so this thing over here, okay? But for my purposes, what I'm going to do is I'm going to arbitrarily center around S2, so keep that as my center, and then look at the distance. So just a rewriting of the covariance, okay? So the point about writing it this way is that if I keep my S1 fixed, just my location in which the covariance is being taken place, I basically have a well-defined spatial correlation function, and I can take the Fourier transform of that, and it's going to be just a well-defined spectral density function. In particular, it's going to be positive, and it's going to be symmetric at the relevant places. Okay, so that's my location-dependent spectral density function. And so one can show now is so having defined what I mean by spatial, the location-dependent spectral density function, I can now basically tell you what the covariance between the DFT at two different locations are going to behave like. So now what we have is you have the DFT at two different locations, okay? And now you no longer get this near uncorrelatedness property. You get this term over here, which is like the error, okay? But you get something which gives you information about the non-stationarity. So you keep basically the frequency fixed, and there's a sort of slight asymmetry in this, and that's just, you can get rid of by looking because of the rounding errors, but you keep one frequency fixed. And now what this thing is there is taking the Fourier transform over space. Okay, so it's a Fourier transform over space. And so essentially what it means is if you are in the spatially stationary setup, the spectral density function is no longer location dependent, the S goes away, and that Fourier transform now will be 0. And so we go back to the original result. On the other hand, if the Fourier transform is spatially dependent, then because we're taking the Fourier transform as space, you're going to see that correlation coming into play over here. Okay, so so this is kind of it. And so somehow this is not too surprising for me, because these results I also saw in the time series setup. So up to this point, it was more just sitting down, integrating, and playing around. It wasn't too hard. Hardness comes a bit later on. Okay, so basically, to summarize the story so far, we have this DFT, okay, the Fourier transform with Matsuda and Yajima defined, and now I found the Fourier frequencies when you're in the special situation of uniform sampling of the locations. From that, you can basically define the analogous version of the fundamental frequencies, which are similar to the Fourier frequencies in the time series setup. And we found out that in the non-stationary, we don't have this uncorrelatedness. Okay, so what I want to quickly discuss is now sort of the useless stuff in some sense. How do I do the asymptotics? Okay, what does I mean to do the asymptotics? And so, of course, in time series, you do the asymptotics by making time increase. Okay, make the time series increase. How do the asymptotics work in the spatial sense? Well, I'll basically use the sort of setup, I think, that goes back to Hall and Patel, may go back even further. And they basically look at the situation where, analogous to the idea that this time series increases, they're increasing the spatial domain. So they're basically blowing up this spatial domain over here. But of course, the number of observations inside there, if we just blow up, it doesn't change. So what we need to do is that we need to blow up the spatial domain, and we also need the number of observations increase. Okay, so n also has to increase. And they make what is known as, they discuss many types of asymptotics. The asymptotic we work under is what is known as infill-outfill asymptotics. So their idea is, okay, let the spatial domain blow up, and let the number of observations in the spatial domain also increase, but we make sure that the number of observations inside the spatial domain are increasing at a faster rate than the spatial domain increasing. Yeah, so this basically lambda d over n is going towards 0. Okay, so it makes you laugh a little bit, because in real life, of course, it never happens. So, you know, kind of stuff. But at least it allows us to understand what's happening to our statistics we have. So that's the way we're doing. We're working in this infill, outfill, mixed asymptotics world developed by Peter Hall and Patel. Okay, so now what I want to do is I want to sort of get slowly towards defining my test statistic. So what I want to do is, I know that there's this difference property between the spatially stationary setup and the non-stationary setup. So what I could do is, given this DFT over here, why not try and measure the dependence, the correlation between the DFTs? Yeah, so like an autocorrelation. Treat my DFT here like a new frequency series and try to measure that dependence here. So what I do is just use look like a regular sample autocorrelation function and define this thing over here. Okay, so it's 1 over lambda, and now the sum. So this thing over here. Okay, the reason whenever I see a talk, I have such a short memory that I always forget what people do, and then I always wish they wrote on the blackboard so I can remember. So I'm just going to write down this definition, and you probably all got great memory, so it doesn't matter for you guys, but for me, it really bothers me. So this is my spatial. This is my in some sense, it's going to be my statistic, and it's this thing over here. And I will discuss it in detail later on. So this is my, so Jn omega k, Jn omega k plus r. Okay, we can sort of generalize this idea and not keep the weight constant. So we can weight the frequency and generalize a little bit more and make a weighted DFT and its correlation. So this is the sort of more general version. It's one I'll be talking about later. And how we choose the weights, I will discuss when I start discussing what the alternative looks like. So this is my statistic. And of course, in order, you're trying to look for decorrelation, you mean where it doesn't look correlated. So this is defined for R not equal to 0. It makes no sense looking at R is equal to 0. It's like the variance at that point. So R not equal to 0. Basically, the DFT at different frequencies over the shift. Okay, so that's my test statistic. And of course, this is the general test statistic now in the spatial domain. This is how I'm defining this thing over here. And now, before I start talking about sampling properties, we have a problem that I never really encountered in the time series setup. It's my indice A. It looks kind of trivial, but it really matters in how you approach this whole problem. If your A is equal to lambda, so that basically means, so you're really in two situations. If A is equal to lambda, what does that mean in terms of the DFT frequencies that you're looking for decorrelation in? That basically means you're going from 1 over lambda to basically lambda over lambda. So you, in some sense, if you're only letting your frequencies go from minus lambda to lambda, you're looking at, you're saying, okay, I'm going to blow up my frequency domain, my spatial domain, lambda increasing in astronaut means it's just blowing up. I'm going to map it onto my frequency domain, but I'm going to really limit the frequencies I'm going to be doing the analysis over a very, very limited domain, basically from 0 to 2 pi. That might be okay, but if you're testing for non-stationarity, you're testing for stationarity, you should be looking for correlations in some sense everywhere beyond this very restricted frequency domain space. So you really should be looking at a situation that the frequencies domain is also increasing in the same way that the spatial domain is increasing. So what does that mean? Well, that basically means that now you're looking at, now we're looking to A over lambda to A over lambda, okay? And you want your A now to grow much faster than lambda. So that means that, okay, your spatial domain is blowing up, and also my frequency domain is blowing up, and I'm looking at correlations now in much higher frequencies, okay? And that's sort of fine, and so in some sense, in this setup over here, it really makes sense to look at the setting where your frequency domain is increasing. But this can cause an almighty problem when you're trying to calculate the distribution of your statistic. So in the case that your frequency domain is completely fixed, everything is very easy to work out. You now have the number of indices is lambda, so now you say, okay, well, I use that decorrelation result I had previously, I take the expectation of this monstrosity, and I kind of work it out, and now because there's lambda of these terms over here, I have 1 over lambda, it's fine. My statistic that I'm looking at is going to have an error which is of order 1 over lambda. That's what I'm looking for. That's fine. It's an analogous time series situation. Okay, but now you say, okay, well, suppose I let my frequency domain blow up. I do the same calculation on this, and things get really messy. So now what you have is you have a situation where now you have A order of A terms, and A is much bigger than lambda. And you sit down, you plug everything out. My students told me a new word called chug and plug. And so I do the chug and plug in this case over here. And I get now A over lambda squared. And I want this quantity to be small. So in order for this to be small, it's very much restricting my A to be of order A over lambda squared, which really suggests in some sense I can't increase my frequency domain too much. And if you think about it a little bit further, okay, this is just the expectation. I need to work out the variance. I need to start showing CLT on this monstrosity. If I work out the variance, this thing the restriction becomes even worse and even worse. And I go back to the fact that I have to have my frequency domain the same size, not increasing, which is not what I wanted. So it's the first time in my whole life I sat down and did some simulations. I did some simulation. I mean, normally I have to be it's at the end of the paper, but this time I really wanted to make sure what was happening. Simulations suggested otherwise, which meant that somehow my chug and plug method that I asked up there was really not. I need to look for a different way of going about it. So I'm not going to tell you the whole proof. This is cumbersome and takes forever. But I want to give you a sort of feeling of where all this comes from. If you don't care, you can just tell me you want to go home. That I can also deal with that. It's not a problem. But to me, it's interesting. But before I give you the voting on whether you want to see at least the feeling of the proof, I want to consider now sort of general types of statistics. I'm not saying that these are sort of I'm proposing stuff, but it sort of unifies the stuff that maybe other people have done. What I want to do is sort of consider statistics of the type over here, sort of weighted DFTs in some sense. And the reason to me they are interesting is that, for example, if R is not equal to 0, it includes the estimated correlations between the DFT, which is exactly my test statistic. In the case that I let R is equal to 0, so I put R is equal to 0 up here, I get this thing over here. And if you are sort of familiar with time series analysis, this looks a little bit like your estimator of your covariance function, a lag V. And this is true. This is really what it's estimating. But in order for you can show later on, I'll just roughly say, you need for this to be a consistent, a proper estimate of covariance, that this frequency A must also be blowing up as lambda blows up. So you really need to set up the frequency domain needs to blow up too. So, you know, in this statistic over here, you also belong to this case over here. There's also the analogous version of a Whittle type likelihood. And now going back to the paper of Matsuda and Yajima, they considered a sort of Whittle likelihood estimated like this. Their only difference was that, well, they didn't assume uniformity, and that matters now. I'll discuss why later on. But their estimator was not a summation sign. It was actually an integral sign. So theirs was just an integral over the frequency. And they actually said that in implementation, they would have to discretize it, but they didn't show any results on that. So that's kind of what they do. So they look at the integral and they look at the properties of that. So of course, the Whittle likelihood goes under this situation over here. In this setup over here, though, you don't want the frequency domain to blow up. And there's a reason for that, because basically you're looking at the logarithm of spectral density function divided by the spectral density function. And as you know, the spectral density function is Fourier transform of the covariance. Is a well-defined monster, which basically means as you increase the frequency, the spectral density is going to go to 0. So if you take the inverse of that, it's going to blow up. So in their setup, of course, and also if I'm looking at it too, I need to keep my frequency domain fixed. So in this setup, you need the frequency domain to be sigma lambda. Okay, and if you are familiar with time series, these are like Fourier type statistics, which we use 1 a penny in time series. The only slightly different thing between this setup and the time series setup is in time series we have an analogous version. We define a statistic maybe in the time domain and the frequency domain. We can go between the two. It's not so clear how it works here. There is some way of going between the two here. Okay. Okay. So. I ask you, I mean, would you like to know why things work when you blow up the frequency domain, or do you truly not care?
Just go ahead.
Is it okay? Okay. Then I have to unfortunately write on the blackboard a little bit, if you don't mind. Okay. So this terrible proof you see here is very nice because it's what I call a sort of a brute force proof. You just go in and there is another way of proving this result, and the advantage of going the alternative route is then that alternative route basically everything is equivalent, but that alternative route allows you to do analysis pretty much for everything we do so far. So that's basically the trick, to go an alternative way for proving this result, and that's what I just want to explain to you very briefly right now. So just to summarize, have I broken this mic? I could have done. Okay, I apologize. All right, so this thing over here, if you remember, is roughly speaking to you remember, is equal to 1 over lambda minus lambda over 2 to lambda over 2. This is basically the domain of the spatial domain I'm defining here. C S1 minus S2 e to the I S1 minus S2 omega K1, and then it's going to be e to the, maybe I don't want to write it quite like that. So 1 second. So it's going to be, so let's write e to the IS1 omega K1 e to the minus IS2 omega K2 ds1 ds2. Now, if you're working in time series, often what we do is we look at our covariance, and because we don't like to think in terms of covariance, we just turn it into a spectrum. We turn it into an inverse Fourier transform. So what we know is because f omega is basically equal to the Fourier transform of the covariance function. So I do everything in d is equal to u, but I've done it all in the other way too. So this is a Fourier transform. So then you can write Cu as so infinity, infinity as the inverse Fourier transform of this, which you can also very easily do. Okay, so what we do is we stick that into here. So now what we do is we just go minus infinity to infinity, which is basically thing. We put here x, okay, and then we have e to the I. So now what we're doing is we're sort of breaking up or splitting up frequency from the spectral density, frequency from the process in some sense. So that's basically S1 omega K1 plus x ds1, okay, and then it's going to be integral minus lambda to lambda, lambda 2, and this is e to the I S2 omega K2, there's a minus sign over there, plus x, and then it's ds2, okay, so we don't think. And basically, if you're a little bit familiar with Fourier stuff, basically what we have is just the integral of the e. So we know that 1 over lambda minus a over lambda to a over lambda e to the I, e to the I s lambda over 2, so this is, sorry, lambda over 2, this is lambda over 2 over here, e to the IB, so basically the Fourier times the exponential, this is simply equal to sine lambda over 2b over lambda over 2b, which, if you're familiar with non-parametrics, looks very similar to Dirichlet kernel, but Dirichlet kernel defined over R, and what math people like to call this, they like fancy functions, they call this a sinc function. This is the sinc function, lambda 2 over b. Okay, and the sinc function happens to be the thing that sort of saves us a lot. Okay, so we're basically, the whole thing is I basically get this df correlation with near t and I transfer it into sinc functions. Once I have my sinc function, this whole thing over here is completely, utterly disorganized. Okay, we'll manage somehow. Okay, once I have this thing over here, okay, what I have now is that basically I have that if I start to put this thing over here, this thing over here becomes lambda over 2 pi f of x. Now my sinc function, lambda x over 2 plus k1 pi, and then it's going to be sinc function, lambda x over 2 plus k2 pi, and it's going to be dx. So basically now I've got rid of my location, I'm just down to a bit of algebra essentially. So now the only thing that I want to do is I do a quick change of variable, and I explain to you quickly what you do. I won't tell you the details. So it's essentially now, it's a lot more cumbersome than the other proof, isn't it? So now what I do is I do a change of variable, so I let lambda x over 2 plus k pi equal some u, and so basically if I do that, I start to get where I want to be. So I get f2 lambda over 2 minus omega k1, and then this is going to be my sinc function at u, because this is equal to u, okay? And then it's going to be my sinc function at u plus k1 minus k2 pi du. Now, if any of you played around with sinc functions a little bit, they have a very, very nice property. Sinc functions are orthogonal to shift. which basically means if this thing were not there, this would be equal to 0, and that's giving us all the gain. So you probably all know this. It took me a bit of wolfram to figure it out. So basically, I get that. So this thing over there, so if k1 is not equal to k2, this basically becomes pi f. I'm going to call it omega k1. And then I have the sinc function playing a role. Sinc u plus k1 minus k2 pi. And then it's going to be that difference. And you can see now kind of where everything's going to come into play. But I'm not going to give you too many details because you're probably bored of it now, right? So minus f2 omega over lambda. Okay. I mean, that's not lambda, it's omega 1 there, omega k1. And then it's giving my sinc function here. Okay, so now the whole thing is, it's basically, but it takes a little bit more effort than that. You basically do a Taylor expansion on that. Okay, you do a Taylor expansion, you get the 2 pi over lambda coming out, you play a little bit, and that's where you're getting your bound. And that's the trick. Now, it looks like a very, very cumbersome way of proving the result, and I completely accept that. But somehow, and this surprised me a little bit at the beginning, the beauty of the sinc function is that essentially now, when you start playing with looking at not just the expectation, hello. So now I won't, I know that I'm running way over time, so I probably will try not to. But now, using this technique over here, you can start playing with that up here, and that now summation you have over there is no longer painful. You can really deal with it in a nice way using the same method over here. So what you can show now, going this route in a lot of pain, is that when you take the expectation of this, you get basically 1 over one over lambda log a lambda over n plus this thing, some small terms over there. But it's basically saying you don't need this huge constraint on the frequency domain not increasing that fast. The frequency domain can pretty much increase at a much faster rate than the time than thing. You've got this gain going on over there. And interestingly, what you have now is that you also get what happens when r is equal to 0. When r is equal to 0, fundamentally what you're estimating is the Fourier transform between spectral density function and your weight function here. So now if you're into time series, what you say is, okay, put my weight function here to maybe be exponential, and then you get inverse Fourier transform, you get your covariance. But that's basically why it's nice for me. Okay, and so using this same type of technique, but even more pain, you can start getting now the properties of this thing. You can show, don't worry too much about thing, that you can show that remember, when r is not equal to 0, you've got a complex random variable. So you can show that the variance of the real part is the same asymptotically as the variance of the imaginary part. The variance of the real part and the imaginary part is asymptotically uncorrelated. And the variance of, and also the variance and the covariance at different lags is asymptotically correlated. So we have a sort of statistic which is uncorrelated at different lags under stationarity, and also the real and imaginary parts are uncorrelated. So now we can start to do things a little bit. So don't worry about this, it's just notation. And also using the same techniques, I'm working, and everyone will complain about, under Gaussianity. Okay, I'm not using mixing. Probably could use mixing, but I'm working under Gaussianity. And then you can basically get the asymptotic normality of the whole result. So basically, I did very painful. I did a cumulant proof on this whole property, and once you can show the cumulants go to 0, you get normality of this whole thing. Okay, so let's go back now to application, and that's basically testing for spatial stationarity. What I have, as you recall, I have my weighted DFT autocovariance over here. I want to know what it looks like, and basically I told you that under stationarity, if r is not equal to 0, this quantity here is going to be close to 0, so it's pretty much uncorrelated, it's estimated as 0. And we have a CLT too. So basically, if I look at the real and imaginary parts over a whole bunch of r, okay, so basically, oh, I've taken my picture off, but there are a whole bunch of on the grid. This quantity over here, I just have to standardize here by a matrix, which is simply a diagonal matrix, okay, and then a weight function, which I'll discuss a little bit later on, just a weight. That's all I have to estimate that. This over thing is going to be asymptotically normal. because I got my normality results using this infill asymptotics and also A growing large too. And then I can define my test statistic. What I have is these weighted covariances at different lags R. And so I use as my test statistic an L2 norm of that. So I take basically the L2 norm of that. And basically my L2 norm you can show using just basically, so long as I keep R fixed, that this is going to be asymptotically a chi-square distribution where the number of degrees of freedom depends upon the number of R multiplied by 2 because I'm looking at the real imaginary parts. Okay, so there's basically. So I have my test statistic. Okay, so since this is the sort of change points in related areas, now let's go to sort of related areas. What does my DFT covariance look like under non-stationarity? This is really frustrating for me a little bit because I thought, okay, at one point in my life, at least I can get away from local stationarity. You know, I'm doing something that's got nothing to do with local stationarity. So then I started thinking, okay, like what is this thing estimating? And of course, you're in a non-stationary setup. So you're letting your field grow, okay, your spatial, look at my thing, my spatial domain grow. Okay, in stationarity, that's fine. You know, the covariance here is going to be the same as covariance here. In the non-stationary setup, you let your spatial domain grow, okay? Your covariance here is going to be really different to covariance here. So when you use the asymptotics and the spatial domain grow, you don't know what you're estimating. So what I had to do is go back to my old friend, the rescaling device, which if any of you work with local stationarity is our friend and tool. There's no as such local stationarity going on here as such. I mean, you could play around with it, but basically I use rescaling in order to get over this idea. So I need to go into another universe which uses scaling. So my motivation goes as follows. If you remember, I defined in the non-stationary setup this location-dependent spectral density function, which is basically your covariance located at S and the covariance all shift around there, and you're taking the Fourier transform of that. That's this F omega over here. Okay, now remember, I'm looking at a spatial domain which is fixed, which is basically 0 to lambda or minus lambda 2 to lambda over 2. So I can take the Fourier transform of that, and so, because F is bounded, it belongs to L2, so it has a Fourier, the Fourier representation of this thing over here, which is the Fourier coefficient. This is alpha lambda j, and that's simply the Fourier transform of the spectral density function. Okay, right. And this is the problem. I can't estimate anything because these Fourier coefficients change with lambda. In fact, they blow up with lambda. So they change with lambda. It's really, really frustrating. So to get over that problem, I go to my rescaled universe and I say, okay, let me keep my Fourier coefficients fixed. You know, I increase my spatial domain, I keep my Fourier coefficient fixed. What's happening in that? So when I do that, basically here, what I'm playing with is a sequence of spatial random fields now. So I'm in another universe. I mean, this is not happening in real world here. But I keep a spatial, but this allows me to see what is my test statistic actually estimating under non-stationarity. So I keep my Fourier coefficients fixed, but now each time, for a different lambda, I get a different location-dependent spectral density, and that's this thing over here. If you work in this rescaled universe over here, you can basically now show that your Fourier coefficient is basically estimating the Fourier transform of this weighted spectral density function. It's sort of meaningless when you just look at it like that. Don't worry about this bit over here. It's just bits that come out due to edge effects. I mean, the thing. But basically, in the setup that we let G omega equal basically the exponential shift V, okay, then this whole thing becomes quite clear what it's estimating. It's simply estimating, so your thing is going to be estimating the covariance, spatial covariance at lag V. So you keep your lag V fixed and you look at the spatial covariance at this point at lag V, this point lag V, this point, and you take the Fourier transform of that. And this DFT, weighted GFT is estimating that quantity over here. So that's basically what it's looking for, changes in your covariance at lag V. Okay, so now you kind of know what the test is actually trying to detect. It's detecting those changes over here. It is, I told you, I wanted to work in non-rescale time, so I did look at what happens in the non-rescale time. It's not clear what you're estimating as AG, R is estimating anymore. but you do get some sort of power. You can show in some sense that you get sort of power in your test. Okay, so I'm going to, so basically practical issues, this is what your test statistic looks like, okay? So the only thing that has to be estimated is this C lambda, which is this thing over here. It's a bit of a pain to estimate. I look for dirty ways of doing my coding. This is pretty unpleasant to estimate. So what I did was basically, because in the stationary setup, these ANGRs are uncorrelated random variables, all roughly speaking the same variance. I was estimating a lag R, so I would use the A's at later lags and try to use that as a proxy. So those at later lags, try to get the standard deviation from there and use that as my estimate of this. It's very dirty, kind of works, gives you good type 1, but you kind of lose power in some sense when you do that type over here. But that's what I try and do, because I really like my coding to be as fast and dirty as possible. One issue here is computational speed. So I work in time series, and in time series, everything can be done FFT, so your speed of everything is very, very fast. Your DFT is very fast to implement. Here, I cannot see any way of getting the spatial DFT in anything less than n squared operations. It's kind of painful to evaluate. There are some engineers, they work at IEEE, they tell me that you can start working irregular spacing, you can get faster speed. Maybe you can. I should read their papers a little bit. So there's this problem that you don't get the speed that I would have liked so much to get this quantity working so much. This is something when I'm coding, I should probably learn to see at some point in my life. One of the assumptions we've been working on is uniformity, a very natural assumption, which is what Matsuda and Yajima were working on, and maybe that's why they didn't do the discretization so much, I have no idea, was that your spatial domain may not have uniform sampling, and then you do not get the uncorrelated property, then just things don't work. There is a dirty way of getting over that trick, and that's dividing by the density of the dimensions, and then you sort of go back to uniformity. Whether that will work in practice, I have no idea, but it's a dirty way of trying to uniformize your locations, and this is one possible trick that may possibly work, I'm not sure. And I think that's it. I'm sorry, I went over.
Thank you very much. Questions? I'm thinking about the time series case. Instead of testing for stationarity, quite often you test for a unit root.
Oh, so what happens in this case over here?
Yeah, because I know Materon and these guys, they are looking at non-stationary fields. And are there something corresponding to the unit root test?
But their null is unit root, isn't it, when they're playing with? So their null hypothesis is unit root against the alternative.
Yeah, sure, it is, yes.
So I'm not sure.
Does anybody know? Is there something analogous to the unit root test for random fields?
I think on lattice.
I see.
There are some people who are, some Hungarians working on this. Unit root on... Just because he's a token Hungarian here. I do know there's some Hungarians working on the unit root on lattice. I refereed some papers by them, but yes, yeah.
So my students worked on something like that one. So if you need a data set, we have essentially a very, very large one. So the state of Utah is collecting daily temperatures 5 times a day at 230 locations there.
Not uniformly distributed.
Of course, okay, because there are certain parts that nobody lives.
Yeah.
So if you look at it, okay, and then you just go in and you try to do like, okay, so fit this modern curve, of course it will not fit. So in this case, okay, you just look at the data as it is, it looks extremely non-stationary. But it turned out, okay, that the problem is when doing the analysis there, that instead of the mean, there are further things, okay, which are essentially not random. One of them is essentially like, okay, the elevation, okay, which must be counted for. The next one, what we have to look at it, and it's very interesting, this is the strength and the direction of the wind, which again provided there. After this is taken out and taken into consideration, surprisingly, okay, it looks essentially very, very stationary. So what we did is essentially we cut the whole thing into parts there, we estimated, okay, the parameters for this matter index there, and they were essentially the same. So it was interesting there, so we wanted to predict.
So you used a rolling window, so to speak.
Yeah. It's something like that one bell. Okay, so like moving and doing this one. And in this case, the interesting thing is that there is a part, and this is the northern part of Utah there, when essentially 70% of the stations are extremely close to each other. And then when you are going away, then in this case, yeah, they are getting very, very sparse. And the interesting feature of this one here is like, there are, okay, so stations there, okay, so which look very, very close. And when we are using the measurement, okay, that's essentially what is measured between them. It got absolutely no relation because there is a very, very high peak between them. So you really have to look for this type of thing. But if you would like to have a data set,
Huge data set.
and I would like to point out, okay, because we are nearly a perfect rectangle. Yeah.
Other comments? Okay, let's thank Suhasini.